You're listening to the Future Tech Podcast with Richard Jacobs. Future technologies such as artificial intelligence, stem cells, 3D printing, gene editing, Bitcoin, blockchain, the microbiome, quantum computing, virtual reality, and exploring space are much closer than you might think. In fact, many early versions of these technologies are in play right now, and the companies that are using these technologies are the focus of this podcast. My goal for you, the listener, is to learn from these podcasts. You may very well learn something that may change the course of your life for the better, steer you towards a new career, or give you insight into addressing a thorny medical problem. Remember, this podcast and its content is informational in nature only. No medical, tax, legal, financial, or psychological advice is being given. If you enjoyed the podcast, please listen, subscribe, like, and tell your friends about it. Thank you. Hello, this is Richard Jacobs with the Future Tech and Future Tech Health podcasts, and I have Albert Liu. He's part of the MIT research team in the lab of Professor Michael Strano, again at MIT. Prior to joining MIT as a presidential fellow, Albert had worked with the late Professor John Roberts on developing novel NMR, nuclear magnetic resonance, spectroscopic techniques to probe functional group interactions. Functional groups are parts of a chemical that have a function or interaction with small organic molecules. He spent 2 years in Professor Gregory Fu's laboratory learning reaction methodology development, and he developed a new method for the catalytic asymmetric synthesis of alkyl boronate esters. Well, I got through that pronunciation, but excellent. So he's got a pretty extensive background in the lab, and what we're going to talk about today is how the lab of, Strano's lab's working on cell-sized robots that can sense their environment. Interesting topic. So, Albert, thanks for coming. How you doing?
Pretty good. Thank you for the invitation. It's a pleasure.
Yeah. First question, when you say cell-sized robots, how big is a cell? A human cell, for instance, and what are the dimensions of it? The radius or the other dimensions of a human cell?
Right. Of course, human cells vary in size, but the target we have in mind are approaching the size of a red blood cell, which is typically with a diameter of 7 to 10 microns. So that's about 10 times 1 millionth of a meter.
Okay. So you're trying to fabricate robots. Are you trying to fabricate robots from tissue, from organic matter, or from, inorganic matter?
Right. So our target is to do this, to fabricate this robot thing using entirely inorganic matter, the uniqueness, I would say. Yeah, there's related fields where making cells and engineering cells from a genetic point of view. So that would be taking up a biological cell and engineer its genetics in some way and have it have some spectacular functions. And this is different in nature from what we're doing. And we're trying to build this from a synthetic point of view. It's entirely artificial, and there's no living component of the cell per se. Yeah.
All right, so you're trying to do entirely artificial. What would be some of the uses of what you're creating? How would they work? Would they work only in the body, or would they be used in industrial applications?
No, I think the advantage of having sort of a dead or artificial system is that it can be used in a variety of different scenarios and environments. Of course, if you have something that is living, it typically lives in its, natural environment, be it the human body or whatnot. But if something is, inorganic in nature, we actually are targeting a variety of different places, such as the human body, of course, but also within a chemical reactor, which is super hot, humid, and could be very pressurized, or we can send them into distributed locations, such as the soil matrix for nutrient detection and oil pipelines for these sort of gas and other exploratory work. So a variety of different scenarios where it involves a sort of a inaccessible location previously, so to speak. Yeah.
But why cell size then? If it's not going to be in the body, what's so special about that size? Is it just a nice milestone to reach, or?
Yeah. So in terms of the human body application, of course, approaching the size of a red blood cell is super important, because if you can imagine anything that is really larger than a red blood cell will be clogged in your bloodstream. So if you are imagining any biomedical applications within the vesicles of the sort of the inner vasculature of human body or any mammalian system, it's going to be problematic. But of course, looking broadly in the environment, there are a lot of places that is inaccessible to us just because that they are small, right? So like the crevices of the earth where people are like sending these probes into trying to detect for oil and gas applications, or even just small chemical reactors. I think there's a general trend in the chemical fabrication industries to distribute the fabrication of fine chemicals into distant locations where we involve a lot of what is called a microfluidic device. So these are very, very small tubes and pipes and valves where where the chemical fabrication can be enhanced because of its enhanced heat transfer and reactivity, just because it's in a small sort of a high surface area to volume ratio kind of thing. But if you imagine trying to probe what is going on inside is just as much as difficult as to probe what is going on inside the human body. So having it being cell sized actually is very, very advantageous for a variety of different applications. And of course, the human body is something that is of target.
So what are some of the challenges with fabricating little robots at that size?
Right. So I think there are two major branches of the challenge. The first one is, of course, energy. So if you think about it, if you want to pack our conventional electronics into the cell size, it's really not going to be able to hold much of a power. Thinking about conventional energy storage ideas such as like lithium-ion battery or supercapacitors. So energy is the first challenge. How do you power the system with incredibly small voltages or with very little juice in your device for a prolonged period of time, at least, through the span of your exploratory work. So energy is a great challenge for small electronics and also the fabrication. Because of course we can fabricate today incredibly fine CPUs with like very, very well-defined transistors and other electronic stuff at extremely small scale. But if you were to distribute your electronics into the environment, let's say, into the human body or even into the soil matrix and like the Earth's crevice, your device is not going to be able to be very expensive like our computers, right? So you're going to have to mass produce them. So to be able to produce exquisite cell-sized robotic systems and computational systems with this capability of scaling up and mass producing them is also a challenge. So how to integrate everything together at that length scale, stuff like that. Yeah.
Yeah, I would think, I guess you can't use traditional manufacturing methods. Maybe you'd rely more on 3D printing or chemical vapor deposition or other methods where you can do things that probably learnings from the semiconductor industry would be tremendous here, because I guess the average size of a transistor now on a wafer is nanometer scale, and they're doing tiny features.
Yeah,
is it possible that you could manufacture little robots just like you manufacture chips on a wafer or transistors on a wafer? Billions of them, and then somehow chop up the wafer and they go to work.
Right. So it is technically possible. There are many people, I think, other groups elsewhere in the world who is trying to dice up these silicon chips and into very, very small segments. And I do see a huge potential in doing that. I think it's a promising field. One challenge associated with that is a lot of our conventional materials does not take up the challenge because they're optimized they're incredibly small, but they're optimized for processes that are operated on a macro scale. So computers actually do not work very, very well, if they're diced up into tiny segments like that. And in the material science field, people are working very hard to develop novel materials that are more accessible to us at that length scale to function sort of autonomously on their own. And some of these examples, are like two-dimensional materials that are electronically just as good as silicon, but they are a lot more air stable and they can interact with the environment in a more precise manner than silicon. So the short answer to the question is, I think there's a lot of merit of the current standard of the semiconductor industry. And I think if we can also leverage the utility of the novel materials with these traditional, more established techniques, I think we can make a lot of progress.
So what's the first type of application that you're going for? Are you targeting really specifically, or are you just, what stage are you at? Have you made robots? Are they being used in a certain application?
Right. So just within the past year, 2018, we published two sort of landmark papers, one in Nature Nanotechnology, one in Nature Materials, and both of them are two iterations of what we think could be the prototypes of these cellular electronics or robotics systems. And for both of them, we actually have two slightly different target applications that has already been demonstrated. So one of them, the earlier nanotechnology one, was on what we call aerosolizable electronics. So these are because the size of these computational systems are so small, they can be lifted off in solution and then later nebulized into the air in terms of to be embedded in a droplet of water. So they can be aerosolized. And then what we actually did was to send these aerosols within a pipe, and then they can travel in the pipe sort of with the airflow because they're very, very light. And they can detect the chemicals that is inside the pipe. Not only can they detect different chemicals, they can actually respond also to light. So they can sort of do a very simple logic computation, sort of like an AND gate. So you can see light and the chemical, and when they come together, they will record in this 1-bit memory that is on board. So it's sort of like basically with this type of device, you were able to see after the fact whether your robot has seen the light or the chemical. So that's the very first demonstration we did with this is like what we call aerosolizable electronics. And then later on in the later Nature Materials paper, robotics, and there the applications we demonstrated were to, instead of launching, well, they can also be launched in the air, but they can also be launched into the water body. So like they will travel in the fluid and detect different various chemicals. They can respond to magnetic field. You can gather them and distribute them as well. And specifically, I think what we did was through the soil matrix, we can detect nutrients that are good for the plant and bad for the plant. And so like, for example, I think specifically we detect like gold nanoparticles, which are heavy metals that are traditionally thought to be bad for vegetations and plants, and also zinc cations, which are thought of as a nutrient for the plant. So we can sort of deploy these robots. They can detect these chemicals. They come back. We can then query them electronically or optically, well, both actually electronically and optically, what they have seen. So yeah.
Interesting. Okay. So again, how far along are you? Have you created, for instance, the aerosolized, microbots, and have they been tested in application and worked?
Right. So basically, these three applications that I just discussed to you about are the extent to which we sort of have published, and like we really want to talk about sort of restrict the discussion within the realm of stuff that we have already published about. And so far, I mean, like they have been fabricated and they have been launched inside a sort of a confined space, because we don't want to really get into the discussion of, whether it is safe to have them flying all the way through the air, right? So like they're in principle aerosolizable, meaning that they can be aerosolized.
That's actually what I was going to ask you is, there could be a danger with these kinds of things, but there also could be at some point a lot of pollution, just like we're, polluting the orbit around Earth with all kinds of satellites and junk and everything. What happens if enough companies or ventures do this kind of thing and we have, nanobot pollution? And what would that do, for instance, to if that stuff built up in the human body because it was in the air or in the water or, who knows what happened with the accumulation of that stuff,
Of course. I think these kind of ethical and environmental considerations are very valuable. And it certainly should be brought into the discussion for, policymakers or, even scientists such as we are when we're fabricating stuff like that. But I do think, it is the, as responsible sort of manufacturers, stuff like that, we should make sure that there's a way to clear these things out if you're going to inject them in. That's sort of our view about this. If they should only be used in a manner that is controllable. And of course, I think for any technology, there's a risk for things to be, getting out of hand if they're not being applied and used in a responsible manner, right? But also that should not stop the progress of making incredibly small robotic and electronic systems that are potentially really beneficial and revolutionary for the field of exploratory environment and medicine.
Yeah, that's true. That's true. So, what have you noticed in the the aerosolized bots in a pipe solution and some of the other solutions you worked on? Any unexpected outcomes?
Honestly, not really. I mean, we anticipated a lot of the very reason of us launching them into these pipes is for them to be sort of contained, and a lot of the outcomes have been accounted for. So what happens was that the what we call colloidal electronic systems are aerosolized, and they are launched within the pipes, and they travel with the airflow, and we always have this thing at the end to block it. So what normally happens is that they will just travel, and then they will adhere to the surface that we use to collect them, and then we can take that out and query them using further down like electronic probing and or optical measurements and stuff like that. So what we have found out, scientifically, they are incredibly accurate, and they are able to perform the tasks that we have prescribed them to do, such as the simple computations I was talking about. And so they behave extremely normally. Yeah.
Okay, interesting. What interesting things did you learn from using the nanobots? What did you see that you hadn't seen before by having them flow through a pipe, or is it just proof of concept to see if you can get any data?
Currently, the studies we are having are still in the proof of concept stage. But as a graduate student, I've learned, a tremendous amount from this experience of making these. I think people wants to call them nanobots, but what we call colloidal electronics. But these are just names. There are many things I didn't realize after performing the work, is I appreciate how much energy that we're lacking at this microscopic regime. Like we have energy crises here and there in the world every day on the global and macroscopic scale, but if you actually want to power something, at the cellular level, it's actually incredibly hard. So, and no wonder, biological systems went to chemicals because, chemical structures are incredibly energy dense versus if you look at the energy density of our current electronic systems, if you use the battery used for cell phones, they're going to be depleted at the cellular level within a fraction of a second at the rate you're using them for. So what I have learned, I guess, after several years of working with this stuff, is one of the most valuable lessons was that we should change our thinking of these small systems, even though we want the modularity that our modern electronics can bring. But what we really need is a different paradigm of thinking of the energy source and how to harvest the energy at a microscopic level in order to power the electronic functions and optical functions that we want these robotic systems to do. And I think this is a valuable lesson that the sooner we realize as a whole field, the better. And it will be more beneficial for us to reach this holy grail of nanotechnology, which is to create useful microscopic systems that can eventually, be used in our daily lives. Yeah.
Well, with cells, remember, sure, they're small and all that, but they're continuously getting energy from their supporting systems, circulation, et cetera.
Right. So
even single-celled organisms, they're constantly hunting for food. So it's not like they have all this stuff all this energy on board that will keep them going for hours or days or weeks. They have a lot of fundamental limitations too. And, what I didn't hear from you is like some of the trade-offs, okay, sure, we can't store a lot of energy on board and all that, but a tiny robot wouldn't need much energy to move, So what about some of the trade-offs that make this even workable?
Sure. Yeah. So another thing that I guess, that is a new realization for myself was that at a microscopic scale, many things that sort of function in our world at this sort of normal length scale doesn't apply. For example, if your electronics is as small as a biological cell, it actually do not need a lot of energy to locomote, sort of translate in space, because it can tag on to the fluidic environment that is around it, sort of like exactly what red blood cells do. There's no, if your blood is moving towards the east, there's no way for you to actually drive your cells towards the west unless you're making some sort of rockets on them or something like that. So even though the physical laws remain the same throughout the different length scales and dimensions, the relative strength of different forces actually change. If you look at how they scale with the length of the system. For example, surface tension and a lot of the surface area related forces are a lot stronger than the forces we use to typically in the macroscopic world to translate a system. And in terms of what you were talking about is the trade-off of an electronic system, a human electronic system, artificial system versus a biological system. There's a great lesson there too. A lot of the stuff we build into our computers and cell phones are highly modular, and they are programmable, and you can sort of unplug a hard drive, even if you want a larger one, and just plug it right in. But a lot of the stuff that biological systems or actual material systems that chemists build are not that modular. So this is actually a whole vision that we have created using these colloidal electronic systems, is that we want to combine the benefit of an electrically engineered sort of electronic system with a typical material science system. You can combine them in a modular manner, sort of building material modules for an electronic circuit. Because what the material modules are good for, if you think about it, is that they're incredibly energy efficient. A lot of things sort of just comes for free, but they're super dumb, and you can't really unplug a portion and just have the system work as usual. Sort of giving you a simplified example. If I had a microscopic particle, that's just a sort of a gel bead or something like that, that is responsive to pH, solution pH, like acidic or basic environment. Right. If you think about it modularly for a pH swellable particle, it's actually incredibly complex, because this particle needs to have a sensor that is, detecting the pH of the solution. And it has to have a comparator to compare its native pH state versus the current pH state. It has to make a decision on whether it will swell or not. And the swelling itself is an actuator. So if you want to have an electrical engineer to engineer a system that behaves as well as a pH swellable particle, then it's incredibly hard. And you're going to have a lot of energy harvesting devices or energy storage device on board that will, take up a lot of space, and your particle, electrically engineered particle, is not going to behave as well as a pH swellable particle. But what is valuable about the electrical engineering approach is that if you had constructed a pH swellable particle with, sensors and comparators and actuators, and tomorrow you come to me and you want to construct a, let's say, nitrogen or oxygen swellable particle, then it's incredibly easy. You can just unplug your pH sensor and plug in this oxygen sensor, and suddenly you've got yourself an oxygen swellable particle. But if you go to the material scientist and ask him to make another oxygen swellable particle, he's probably going to have to, review his math and go back to the drawing board and reconstruct the monomer of the polymer and build the whole thing from ground up. So there's this sort of incredible synergy that exists between what is currently known as electrical engineering versus, chemistry and material science. And we can bring them somehow together and construct a material system that is both energy efficient and integratable, and also at the same time very much modular. This is essentially what we're hoping to do with sort of a bigger vision of this colloidal electronics and outlook of the whole space. And a lot of them, I think, we think it should be enabled by these next generation electronic materials that has the benefit of both worlds. They can operate at the expense of extremely little energy, but also right. they can be plug and play into a more traditional electronic circuit that can be designed and reprogrammed and stuff like that.
Yeah, that's interesting. You wonder if they need to do their job and then come back home and dock with a larger structure in order for them to, in order for them to be effective. That's really interesting. Any last comments about the forces that are amplified at those scales and the forces that are diminished versus at larger scales?
Sure. Yeah. So, if you think about forces in general, there are these surface-related forces, and there's also these forces that relates to gravity. Like F equals ma type forces, and it's the scaling of the force differs incredibly, and actually you can show mathematically at the nanoscale or micron scale. There's an inversion of the importance of these different type of forces. These inertial related forces like F equals ma stuff is actually less important than these surface-driven forces at the micron scale. Whereas in our current daily life, that's not the case, right? Because if you have some like surface tension is a lot less important than the weight of something. But at the nanoscale, things are inverted. And one example, Professor Michael Strano likes to tell us is that graphene, which is this two-dimensional carbon lattice, they're actually incredibly sticky. They're kind of like the sticky tape we have in our current macroscopic world. If they're folded onto each other, they're never going to separate. So it's like a duct tape. So things behave a lot more differently at the micron scale. Sort of a lot of things are surprisingly sticky. And the implication of that, of the surface-driven forces being so important at the microscopic scale, is that if you want to build a robotic system at the micron scale, you never, and you want this thing to be able to grab stuff. And it's anti-productive to build them in the shape of a human hand. Like a lot of the mechanical systems that we have today does not really work at the nanoscale. So what you've seen, in commercials or online pictures or movies and stuff where people constructed nanobots, they have these very mechanical-looking shapes and just look like a shrinked robots today at the macro scale. I think it will be anti-productive to build systems that way at the nanoscale. And I think in the future, the nanobots, as we call it, would look very different from a macroscopic robotic system. Yeah. If you want to make something to grab onto something, you would not construct a hand or just a mechanical grabber. You will be much better off considering to use the adhesion force. If you can chemically or electronically turn on and off some sort of adhesion force, it's going to be a lot more productive than a robotic hand.
Yeah, that's really interesting. It's interesting the differences. Very cool.
Right.
I'm glad you got those insights. I think they're going to be super useful. That and emulating nature, or at least living systems, right. Because those things operate at those scales, and there's a reason why they're effective at those scales. So,
yep.
Very good.
Yeah.
So, what's the best way for folks to learn more about, again, for lack of a better word, nanobots and the lab itself, and maybe to get in contact or read papers that have been put out?
Oh, yeah. So, again, we're located at MIT Department of Chemical Engineering, and the principal investigator's name is Michael Strano, and we have a website. So, any folks that wants to get in touch with us, should email to strano@mit.edu, for example, is the email address for the professor. And feel free to visit our website and get in touch with us, via emails and online links and stuff like that. And our papers are all published and links are provided on the website. Yeah. So
okay. Well, very good. Well, Albert, thanks for coming. It's been a really interesting call. Learned some new stuff. So thank you for being here.
Yeah. Thank you for the invitation. It's my pleasure. Yeah.
You're listening to the Future Tech Podcast with Richard Jacobs. Future technologies such as artificial intelligence, stem cells, 3D printing, gene editing, Bitcoin, blockchain, the microbiome, quantum computing, virtual reality, and exploring space are much closer than you might think. In fact, many early versions of these technologies are in play right now, and the companies that are using these technologies are the focus of this podcast. My goal for you, the listener, is to learn from these podcasts. You may very well learn something that may change the course of your life for the better, steer you towards a new career, or give you insight into addressing a thorny medical problem. Remember, this podcast and its content is informational in nature only. No medical, tax, legal, financial, or psychological advice is being given. If you've enjoyed the podcast, please listen, subscribe, like, and tell your friends about it. Thank you.